Hi and welcome back. This is video 2 of 2 for chapter 13. Now, in chapter 13, we've been discussing Faraday's law and how changing magnetic flux through a circuit that is connected to no visible power source can actually induce an EMF that can drive current around the circuit. What I'd like to do today is to continue examining Faraday's law, specifically in the case of generators. Now, generators take and transform mechanical energy into electrical energy. And we're going to talk about the hows here in a moment. But let me show you just sort of a rough layout for a generator that is more or less looks a little bit like what you would see in a power plant. Um, so here what you'll see is you have these parts of a magnet labeled north and south. This, to be clear, is just a little misleading because magnets are always grouped in norths and souths. You generally do not see a north or a south by itself. It's actually except in some of the weirder areas of quantum mechanics, physically impossible. So what you have here, though, is a permanent magnet, and the magnetic field points from north to south like this, uh, sort of like the magnetic field within a solenoid, like that. Now, the changing flux is provided by a loop that rotates. So you have a loop of wire. Generally, this contains, hundreds of turns. So you could think of it, from a Faraday's law standpoint, as n being large. Okay, and what happens is as this loop turns, the area that's presented to the magnetic field changes with respect to time, and as a consequence, you have an induced EMF, which generates, moving current. Now, as this thing rotates, if you take a look at the setup here, you have one leg of the circuit that is attached to a ring here, and then the other one is attached over here. And they're connected via, these are usually carbon brushes that are loose conductors like this that attach like this, and as this rotates like that, they scrape across it, maintaining their connection, allowing this to rotate. And so this right here would be connected to a circuit, like for example, here's just a light bulb. Now, what's not so obvious here is what's causing this to rotate. So out on this side, where you have something doing the rotation here, typically what you have is some sort of prop, a fan. Okay. Now this could be like, for example, in the case of wind power, this could be an enormous fan that just turns as wind blows across it, and the turning is the mechanical energy that's being provided to be transformed into electrical energy via induction. It could be that you have a steam reservoir like this. So high temperature here and low temperature here. And what happens is as the steam blasts past it, it causes the fan to rotate, thereby taking thermal energy, converting it into mechanical energy, and then converting it into electrical energy. Now, incidentally, this method is used by most methods, or this procedure right here rather is used by most methods in which we generate electricity, specifically coal fire plants, nuclear, geothermal, usually. Although there are cases in which you have geothermal power produced by dissimilar metals, which I don't think is very popular. Generally, geothermal is using the heat, like you're piping water through something that's very hot to generate the steam. Hydroelectric. With hydroelectric, what you're doing is you have water that's that's very high up in a reservoir, and you have a hole, and what you do is you let gravity push the water out this way, and as it pushes it out, it blows across a prop, which turns it, which in turn generates electricity. So pretty much even nuclear, nuclear actually uses a slowly decaying radioactive source to heat water. So, so heat water, turn it to steam, blast it past a fan to provide the mechanical energy. Heat water, turn the fan, blowing water past a fan, and then you have your wind, which just uses wind to do it. You even have the hydroelectric ones that are powered by the tides. The tides come in, and as the tide comes in, the water blows past a whole bunch of small props, which basically are attached to generators, which generate electricity. Really, the only methods that you see that don't involve this step of turning something into mechanical and then into electrical are things that use the photoelectric effect, like solar cells. So most solar power doesn't do that. Although you do have certain circumstances where you use light to heat water to turn it into steam, and then you follow the same process. And then you have dissimilar metals. These are called thermocouples. And the dissimilar metals have a tendency to create a potential difference between them, and heating can be involved in that process, and that generates electricity. So it's these methods, like I said, that don't do this. All right. So that said, let's talk about the physics. And to do the physics of this, what I'd like to do is to imagine. So to do this, let's actually take a look at a problem. So I want you to imagine a generator, and the generator consists of a rectangular loop of wire. Basically, it's a bundle of about 600 turns of wire that's been hammered out into a rectangle. And it has the dimensions of 1 meter by 2 meters, like this. So the area is 2 square meters. Now, it's being rotated in this loop right here, or in this magnetic field right here, with a frequency of 60 hertz, 60 times a second. Now, the magnetic field itself is constant, and it points from, obviously from north to south. 5.31 Gauss, which we know is, 5.31 times 10 to the minus 4th Tesla. So here, if you were to look at this sort of on from the front, this is your loop of wire as it rotates, and we're going to have the magnetic field point down the x-axis, and as this sort of thing rotates, we'll have it rotate as drawn counterclockwise, so our angle is the same angle that we're familiar with when it comes to counterclockwise being in the direction of positive theta. Now we're going to assume that the frequency that it rotates with is constant, and if that's the case, that means that the angular speed it has is constant. And we know angular speed is, how your angle changes with respect to time, which says that, theta really here is just omega times t. So what we're given is the following. Our loop has 600 turns. We have a magnetic field that's 5.31 times 10 to the minus 4th Tesla. The area of our loop is 1 foot, or 1 meter rather, by 2 meters, or 2 square meters. Ultimately, we're going to hook this thing up to an air conditioner, and the air conditioner has a resistance of 3.5 ohms. It's just something there to allow us to calculate I. And we have a frequency of rotation of 60 hertz. Now let's talk a little bit more about that. Frequency is 1 over the period. And we know that for constant angular motion, omega is 2 pi over the period. So the relationship between frequency measured in hertz and frequency or angular frequency is a factor of 2 pi. So now we have a relationship between omega and f, which we'll need. So, that said, what are we trying to find? We're trying to find a few things. The first thing is EMF. And then another thing I'd like to find from this is what the maximum EMF is going to be. Okay. Likewise, we want to find the current. Now, to do this, we're going to use Faraday's law. We're going to use the version that allows us to have loops of wire. So there's a factor of n in front. We have theta magnetic dt. Now, what's theta magnetic? Or not theta, but phi magnetic? Well, that's our magnetic flux, and it's going to look like this. Now, look. N hat points this way. B points this way. So the dot product between the two is theta, or at least it's going to involve this theta right here. Now, B is constant in magnitude. So when I do the dot product here, this is just B times cosine of theta. Now, theta is omega times t. And then we have ds. Now, here's the deal, though. This is constant, and our cosine here does not depend upon area. So we can pull all that stuff out, okay? Which means that you're just integrating the area, which is the same thing as just asking what the area of our loop is, which is A. So this right here literally is the same thing as B times A times cosine of omega t. So my EMF here is minus n times the derivative with respect to time of this, which is B times A times cosine of omega t. Now, B and A are constant. They come out. When you take the derivative of cosine, you get a minus sign and also an omega out as you follow the chain rule. So that's going to kill off the negative here. So our EMF is going to look like this. N times B times A times omega times sine of omega t. Now, we can immediately answer the question, what's the maximum EMF? And the reason why is because that's going to occur when sine is at its maximum. And when sine is at a max, that's when the argument here is equal to pi over 2. And so that would make this 1. So E max would equal to N B times A times omega, which, putting it in terms of the frequency that we have, 2 pi N B A times F. Now, N is 600 turns. B is 5.31 times 10 to the minus 4th Tesla. The area is 2 square meters, and the frequency is 60 hertz. So, were you to plug this into your calculator, 2 times pi times 600 times 5.31 times 10 to the minus 4th times 2 and times 60, you get right about 240 volts. So, we could call this E naught or E max. So really, our EMF is equal to E max times sine of omega t. So, we have this. This right here would be acceptable if you were solving something like this, or this is fine as long as you identify what E max is. So that answers, what's E and what's E max. We have our EMF. Now what about I? Okay. So we have a small resistor circuit here. Basically, it's going to look like this. And so we can just use Ohm's law, noting the fact that V is equal to I times R. So here it would be E is equal to I times R. I is equal to E over R. And so if I were to plug in the form of E here, this would be the same thing as NBA times omega over R times sine of omega t, or, again, E max divided by R times sine of omega t. So your current's a function of time. And what you'll notice about this is that sine varies between 1 and minus 1. So there are going to be times in which your current moves one way, and then times in which it moves back the other way. If you go back and you look at our picture here, you'll see how you have an electric field, or EMF rather, oscillating between positive and negative over time. And that's because it drives it one way and then it drives it the other way. Your current goes from between negative and positive as well. Okay. Now there is a name for this type of electrical circuit. There's a name for this type of current. It is called alternating current. AC current, and this is what your house uses. Okay. Electrical devices in the United States and in the rest of the world generally designed, if you're going to be using a house, to run off of AC, or at some point convert AC to DC, like for example with respect to your laptop when you charge it. In a house in the United States, the electrical current oscillates back and forth 60 times a second at 60 hertz. Okay. So, this is the current that it pulls right here. But out of curiosity, let's take a look and see what the maximum amount of current would be. So I, from a max standpoint, would be when our EMF is at a max. That's 240 volts divided by, so I believe it was 3.5, correct? Yes, 3.5 ohms. So 240 divided by 3.5 is about 69 amperes, which is not a joke. Now, AC current is the stuff that you have to watch out for. If you were to crank up your car, pop the hood, lick your fingers, put one finger on one side of the battery inside your car, put your other finger on the other side, the other terminal of your battery, you wouldn't experience anything. No electrical shock. On the other hand, were you to take and cut the cord off of a lamp, fray the edges, plug it in there, and then grab one cord on one side and one of the other sides of the cord on the other side with your fingers, you would experience a very bad situation. You probably wouldn't be able to let go. And that's because as the current moves back and forth 60 times a second, what it does is to tell your muscles to contract 60 times a second. So you freeze. Okay, that's the reason why people who grab what we say are hot electrical wires, that means that they're electrically charged. When they grab them, they can't let them go, and that's because they're physically unable to do it. That's the reason also why they say if somebody's actively getting shocked, you should use a piece of wood and push them away with the wood, knock the cord out of their hand or whatever. And that's because the wood's an insulator and it prevents you from being in the same situation. This is also how tasers work. Tasers hit you with high voltage, low amperage current, and they oscillate back and forth very rapidly, and they cause your muscles to do the same thing, so you freeze up. Now, so this is how generators work. Now that said, what I'd like to do is to continue examining Ampere's law, specifically some caveats. And I want to find a different form of it. That's the main thing I'm looking at here. This form will serve us when we talk about light. So I want you to imagine this right here as being our surface of our loop of wire. Maybe there's a resistor in it or something like that. This is the direction of out. Now there is the conventional direction for a line integral when you integrate around this closed loop, if you will. And that direction would be counterclockwise. The reason why is because it's defined by the direction of out. And if you were to draw a coordinate system like this and call that y and call that x, that would be in the direction of x towards y, which is positive angle. If you go the other way, that would be in the minus direction. So there's a convention for the direction that you walk around when you take and you do line integrals. And like I said, they're based off of the direction of your surface normal. So let's take a look again here at Ampere's law. And again, we want to remind ourselves that our magnetic flux here is the integral of B dot n hat, ds, right? Maybe our magnetic field's going through here. I'm not really so much interested in this direction. Mainly, I'm interested in the direction of this right here. Okay? Actually, just to be pedantic, why don't we just have it go out like this? Maybe it's coming out like that, the same direction as that. Okay? Like that. Now, let's take a look at E here. Now, E is voltage. Okay? I mean, it's EMF, yes, but it's voltage. And we know that there's a relationship between the electric field and voltage. It goes like this. Okay? Now dl is a path, just like this, except normally it would be between 2 points in space. But look. Our magnetic field is defined by, or at least the flux is defined by, the area here, which is closed. So current is going to be pushed around like this the whole way, and there's no clear place where the electric or where the voltage starts and the voltage stops. And that's because it's continuously changing. It's pushing this thing around in a closed loop. So in this situation right here, our integral is a closed loop. Okay? So if I were to relate this to this, these two, I have, for right now, I'm going to put this in parentheses, on the left-hand side, a closed loop integral of E dot dl. And on the right-hand side, I have a minus d by dt of B dot n hat ds. Now, remember, the direction of our current is defined so that the magnetic field that it creates is such that it opposes changing flux. So just for the sake of argument, let's pretend that this is in the direction of delta B. Now, I is conventional current, but this right here is driving around negative charges. So here, if I were to choose the direction of I based off of what's been drawn, if I were to put it in the DL direction and roll my fingers around, I would have induced current this way that is in the same direction as delta B. That's not good. It needs to go in the other direction. Okay? Now, so the remedy for that is to drop the negative sign here, which allows conservation of energy to continue. And that's because of the fact that we've chosen to use a current that's conventional and doesn't actually represent the fact that you're moving around negative charges and not positive charges. So our Ampere's law now looks like this. And a few lectures ago, I mentioned Stokes' theorem. Stokes' theorem allows you to take an integral around a closed loop of a vector field and write it as what's called a curl. And that's exactly what I want to do with the left-hand side. This is the same thing as del cross E dot n hat ds. On the right-hand side, we have minus d by dt of b dot n hat ds. Now what I'm going to do is to pull the time derivative inside this. Now I'm going to move this to the left-hand side. If I pull this under the ds here, it looks like that so far. Now, whoops, sorry about that, getting excited. So the first thing I'd like to point out is that our unit vector n hat, is a constant. Generally, it has a length of 1. So were I to take its time derivative, I'm probably, at least in this circumstance, and at least in realistic problems that we deal with, I'm going to get 1 right here. So the time derivative of n hat is going to be 0. It's going to be constant. It's the dot product that's a problem. Okay, so just bearing with me that the time derivative of that is the issue. Were I to look at this and distribute my derivative through, using the product rule, I have this, that's 0. So this right here really is the same thing as dB dt dot n hat. There's a dot n hat here, there would be a dot n hat here, which means I can write my integral the following way. Now this is equal to 0 in two circumstances. Either my surface is infinitesimally small, which is not the case here, or this right here is equal to 0. Or the way this is typically written is del cross E is equal to minus dB dt. And this right here is the differential version of Faraday's law. It's also one of the Maxwell equations. So that said, I'm going to briefly talk about those. We're going to talk more about those when we talk about light. But the divergence of the electric field is due to charge. Charge is the originator of the electric field. Curling or rotating electric fields are due to magnetic fields that change with respect to time. There is no source or sink of the magnetic field. Rotating or curling magnetic fields are due to, at least right now, flowing charge. These four equations, this one needs to be amended a bit, and that's one of the things that James Clerk Maxwell did. These four equations define the entirety of electricity and magnetism, and they also show something. There is a very clear relationship between B and E. And to give you a hint, I want you to think about the following. Let's pretend that you had a whole bunch of little point charges that were side by side, and they were stationary. Here's my little point charges. Now, these point charges, when they're stationary, are going to produce an electric field. Whoops. That look like this. Pointing radially outwards in a way that we're familiar with. On the other hand, if I take these very same point charges and move them, I don't see an electric field that points outwards. I see a magnetic field that circulates around it. The only difference between the two situations is one has moving charge and one has stationary charge. Not only that, let's pretend that it's not the charge that's moving, but it's me. If I'm stationary and I'm looking at these charges, I see an electric field. But if I go running by very quickly, the charges appear as though they're moving this way if I'm running this way. And I see a magnetic field. The electric field and the magnetic field are really the same thing. One is seen under motion and one is not. And that's in part what this right here is telling us. That's in part what our Maxwell equations, or at least the beginnings of them, are telling us. Now we'll be talking about this later on. So that's it for chapter 13, and I'll see you in the next chapter.